the interesting thing about this case, if we go to the next slide, in there, that the sea level pressure records were, minimum sea level pressure records were established around 970 hectopascals on 13 March. And the science issue here, in addition to the forecasting issue, is why did this Lee cyclone deepen so explosively very close to the Rocky Mountains? This is a very atypical behavior for a Lee cyclone, which raises the question, is it really a Lee cyclone, or is it a Lee cyclone on steroids, or is it a Lee cyclone involved with something else? And the way I like to do my research is I look for outliers. It's like somebody my age has basically seen close to Avogadro's number of weather maps by this time. And so when I look at a weather map, I say, okay, 3 sigma, 4 sigma, relative standardized anomalies. In other words, I look for outliers because I've seen so many of these things. And then this was a big outlier case. And then it leads to 2 questions. What's the science behind such an outlier? And then what are the forecast implications when you're dealing with an outlier event? So that's how we got started on this. All right, so the next slide, please. All right, so if we just look, I grabbed this as a screenshot grabbed off the NCAR RAL page in their Surface UCAR image archive in there. And so as I tell the students, if you can't find the cyclone on this map, you should be in a different field in there. So you can see the several things stand out in through here. First of all, you have this massive cyclonic circulation centered on eastern Colorado or southeastern Colorado. The other thing is there's no real cold surge, even though you have in western Nebraska 30 and 40 knot northerly winds and so on down into northeastern Colorado. This is not associated with a huge high pushing down, but rather that you have a very, very strong surface cyclone in here. So that raises the issue of what's going on. And you can see that there appear to be some boundaries across Nebraska where between the north-northeasterly flow and the southeasterly flow. So and then there's another boundary appears to be off Kansas, in the center in Kansas, between sort of a south-southeasterly flow and southerly flow, and then a surge of drier air. And the other thing that really stands out is the winds, especially like you look at the Texas Panhandle and eastern New Mexico in there. You've got pennants. You don't see that every day on the surface map. So this is a wind situation. So this is quite the event, very, very deep adjacent to the mountains. Okay, let's go to the next slide. So this is a source from David Roth at WPC, shows the March record low sea level pressure values around the country and the different colors associated with the different events and the years that they occurred. And in southeastern Colorado and northeastern New Mexico set records for this storm. So if we go to the very next slide, you'll see the ones that broke the record for March. That's the area that shows where we had this really super deep storm adjacent to the mountains. So that's a pretty big area when you think about it for the number of stations that set all-time minimum sea level pressure records in March. And so that flagged my curiosity. So if we look at some of the further motivating factors, let's go on to the next slide and through here, we see that it also had a severe weather outbreak associated with it. But what to me struck me as interesting for the plains, this is further west than the usual severe weather outbreak. You're usually not going to see this kind of action in eastern New Mexico and the far western Texas this early in the season, maybe more a little bit further to the east. But that location of severe weather is consistent with the deep storm in southeastern Colorado. Okay, next slide, please. Now, this to me is just remarkable. The area in black outlines the area where wind gusts were over 50 miles per hour. That's a huge area. And I flagged down below a couple of the more interesting surface observations in there. At La Junta, let's see there, 330 at 45, gusting to 77 knots in there. Peak wind, so the peak wind at 77 knots, and there were other very strong wind gusts in that region. So you had hurricane force wind gusts over a broad area of extreme northeastern New Mexico and southeastern Colorado. So this is not your everyday storm. Okay, let's see the next one. Now this is remarkable. Why should that disaster have occurred? What a mess to clean up. You've got a train blown off the tracks in there. So maybe you guys in the discussion can help me understand, why would a train, first of all, be on a trestle bridge up high like that over a canyon with those kinds of crosswinds? So what went wrong? Did the railroad company ignore the forecasts? Do they use a private forecasting service that was not paying attention? It's to forgive a bad pun. Somebody blew the forecast on this one in there. But look at those box cars and train cars down the valley. What a mess. So this is a big deal. Next slide. All right, so let's ease into the science and what happened. So, brief overview of Colorado leaf cyclogenesis. So if we look at the next slide, this is a classic diagram from Paul Main Newton's book in here from 1969. Chester Newton in the 1950s and 1960s wrote some great papers while he was at NCAR on leaf cyclogenesis. And this is one of the figures that he developed, a schematic figure, and the A, B, C, and D. The left panel at the top is A, then B and C on the lower left, and D on the lower right. And then some of the takeaways are indicated on the right. But if we stare at the maps in there, you can see the contours of the ridges approach. That hatched area, by the way, is the approximate shape of the Rocky Mountains. It looks like a shoe boot or something like that, but that's the approximate shape of the Rocky Mountains. And then you have the streamlines and the black lines and the dashed line. I can think of them as the height contours in here. Whoop, something just disappeared. Did everything change over there?
No, it looks fine on our end, Lance.
Okay, so something, all right. But I've lost where my place was. I'm now back to the title page.
Oh, is that your PowerPoint perhaps, and not the?
Well, let's see. Yeah, let's see. So, all right, I think I'm back. Okay. So the critical takeaway here is the lead trough forms due to downslope flow before the ridge crosses the Rockies. In other words, you get the lead trough, and you guys all know this is common. And then a weak cyclone forms in the lead trough and moves southeast parallel to the Rockies. So the initial stages of any kind of classic leaf cyclogenesis, the storm is fastened to the mountains, and in the northern hemisphere, the cyclone will move with the higher terrain on the right to the southeast, and you can see the trough as the lead trough develops. And then eventually the lead cyclone begins to turn to the northeast as the southwest flow develops ahead of the Rockies trough. As the trough begins to cross the Rockies, the lead flow, the lead cyclone develops and begins to turn to the east and then to the northeast. And then the cyclone deepens as it moves to the northeast due to classic quasi-geostrophic forcing for ascent over the low center ahead of the upper level trough. So this is a classic diagram that Chester developed and reproduced in their famous book that Paul Main and Chester wrote. And now, if you think about what I just showed you, this is so atypical because the Lee cyclone, the Lee cyclone on March 13th of 2019 was deepest adjacent to the mountains, and then weakened as it moved northeastward away from the mountains. Just the opposite of a Lee cyclone. So that begs the question: was this a Lee cyclone, or was it a Lee cyclone? Was it a special category of Lee cyclone, like on steroids? Or possibly is there some other process in play that is contributing to what happened on this particular day? So if we go to the next slide, which I think is the title slide. You see it says storm overview. So now I'm going to look at a base reflectivity loop here, manual loop. So if we just go, if we go to the next slide, it'll be a first radar loop. Do you see it?
Yeah, we do.
Okay. So this one is for 6Z on the 13th of March. And so this is from the UCAR image archive. So what I'd like to do is just see they're every 3 hours. In other words, I had to avoid like too many megabytes on the presentation at the storm conference in there. So they're every 3 hours. So when I click on it, does it change on your screen when I click on it?
I'm just advancing it manually, Lance.
Okay, let's just go through it. It's slowly at 3 hours intervals, and then we'll go back to the start. And so you'll see how if go to 9Z now. Whoop, things just disappeared off my screen. So we're on 9Z. So you can see the moisture stream and embedded convection in linear segments and some of the coming up across the Texas Panhandle into central Oklahoma, moving into southeastern Colorado. But note it's pretty dry for the most part in eastern Colorado and through here. So if we go to 12Z, you can stuff is starting. You can see the tilt is developing. Note how the radar storm indicated storms are moving eastward across Oklahoma, but they're still holding in pretty much position across Nebraska. So basically, compared to 3Z or 6Z, you're getting the impression that the whole thing is tilting. And remember, the storm is going to be most intense. I'm looking at 12Z. The storm is going to be most intense at 18Z. And 2 more time panels in there. And you're starting to get some on the west side now into Colorado. So if we go to 15Z, everybody okay on 15Z? Now you can see now you can see the hook developing. You see the growth on the back side and the northerly side of the storm, rapid growth of echoes in between 12Z and 15Z. And that basically, so the dry slot is really developed across Texas Panhandle, Oklahoma Panhandle, into western and central Kansas in there. And now if we go to 18Z at the time the storm is deepest in there, you can see how the dry slot is wrapping around the storm, and you can see some banded structure in extreme northwestern Kansas and southwestern Nebraska spilling into extreme eastern Colorado as the broad circulation has developed in the radar. So this looks like a classic bomb cyclone and not your typical Lee cyclone. But does anybody have any questions before we start looking at maps that they want to bring up at this point before we start looking at some of the maps?
Any questions, just raise your hand and I'll unmute you. Nothing at this time, Lance.
Okay. So let's pull through to the first of some 2-panel slides in through here. On any of these storms, I've learned, because I've lived too long, that you always start in the Pacific. And this is it from a historical note. When I was a graduate student with Fred Sanders at MIT, he was frequently visited by Dick Reed and Chester Newton and Jerry Namias. And I always watched what they did like a hawk. And when they looked at weather maps in the old paper map days on walls, some of you will remember that. I remember asking Jerry Namias, says, when you forecast for Boston, why do you start in the Pacific? I didn't know anything in there. And Jerry would be very patient and said, because what happens in the Pacific is going to determine days later what's going to happen over North America, and particularly over Boston. And so those were lessons I never forgot. So if these are what the guys in the field always started looking at the maps of the Pacific first, and we were in eastern North America, there must be a reason why these guys are doing that, because they're much smarter than I was, and so that's what I learned to do. So in this case, if we look in the Pacific, on the left side is the sea level pressure is in the black contours, and the 1005 thickness is in the dash contours with the change from dash red to dash blue at 540 decameters. and the 200 hectopascal wind speeds are shaded in meters per second, with the first shading light blue at 30 meters per second. So the top color bar at the bottom is the scale for the wind speeds in meters per second, and the bottom scale is the precipitable water scale in millimeters, referring to the right panel. Now the right panel shows the 700 millibar heights in black, the temperatures are in red, and the winds are in the classic barbs, and then the precipitable water is what's shaded. So this is 8 days before the main event, but the noteworthy feature here is, first of all, you have a retracted Pacific jet, and by that I mean that the core of the jet stream is closer to Asia than it is to the Central Pacific and certainly into Eastern North America. And there are a series of cyclones that are forming on that jet, and you can see one in the entrance region of the subtropical jet there. And then it seems like a coupled jet type structure, and the northeasternmost position of the coupled jet is associated with strong warm air advection, which is tightening the temperature grade. So you don't have strong cold advection to the north, but you have deep warm advection ahead of the cyclone to the south. So that's going to tighten the thermal gradient, which will lead to the downstream jet. So these coupled jets that develop sometimes are certainly related to the evolution of the low-level thermal structure, and in particular the thermal advection. And if you look on the right panel, you see you're pulling in about 30 millimeter precipitable water values, pulling it northward and starting to wrap it around the cyclone. And there's a residue, there's a ridge over Alaska in there, and there's a low lower in the subtropics west of Southern California, west of Baja, near about 120, 130 west or thereabouts in there. And so that's the antecedent condition. So now what's going to happen as we go forward on that? So let's go to the very next map, which should be 6 on the 6th in there. Do we have next map up?
Yeah, we're there, Lance.
Okay, so you can see the storm has deepened greatly in the exit, and the jet streak has extended in the western Pacific slightly to the east in response to the cold advection behind the rapidly deepening cyclone. You see the moisture is pulled around to the north. You still have that coupled jet streak, but you still got the big ridge up and over eastern Alaska and northwest Canada. So one has a big ridge up and through there. All right, let's go to the next one. Getting some phone interference. Is that still my voice still okay?
Yeah, you sound fine on our end.
I was hearing like somebody was trying to dial in or something. Okay, so we're now on the 0Z the 7th, and now we have this big hole east of the Kamchatka Peninsula in there from that former deep cyclone. You can see the extent of the aerial circulation, the cyclonic circulation, at 700 millibars over there. But now, and that's helping to keep the Alaskan ridge in place. But now note what's going on over here. Note that the next cyclone in the series is starting to deepen just off the coast of southeastern Japan in there. So and you can see the moisture surge associated with that in the precipitable water field. And you can see what's going to be interesting, you already see there's like a subtropical jetlet, if you will, that's moving it from the eastern Pacific that's extending towards northern Baja California and extreme southern California and Arizona. So you can see that in there. So in each one of those little features, the original storm, the new storm, and the little jetlet in the eastern Pacific are all associated with little surges of precipitable water coming out of the deeper tropics. So this still doesn't look like, why should you expect a big storm in through here? But let's go to the 0Z the 8th, 24 hours later, in there. And what you'll see now is that second storm that was off east of Japan is now deepening rapidly in the left exit region of the now extended Pacific jet. And note the strong cold advection going on behind it, and the moisture surge with it. And you still have this jet extending from north of Hawaii, nowhere near as strong, towards the towards Baja, a little bit further to the south. And you still have the ridge in place. So these series of disturbances out in the Pacific are basically, the story here is we're going to see are keeping you reinforce the ridge and are eventually going to become associated with anticyclonic wave breaking that's going to set the table for what happened on that big event. So let's move on to the 9th of March. And now we have another big hole near the tip of the Aleutians in there. This is going to be like the Groundhog Day movie. I've seen this movie before, and like we replay. So you have that big hole, but note the subtropical jet streak that's still sitting out there. But note the ridging that's starting to develop now. East of the date line, you can see the flat ridge that's building at 700 millibars ahead of that deep cyclone that's moving northeastward across the Aleutians. So let's go to the 10th of March. Now note what's going on. Now note, you'll see the deep low is still north of the Aleutians, but the tip of the jet streak now is in the Gulf of Alaska in there. And if we compare that with what's going on the right, note the strong northerly flow, that northerly jet that's now developed off the California coast, and there's a weak trough off the California coast, weak surface low in there. And if you look at the 700 millibar flow, the thing that really struck me when I first started looking at this is note the indications of the onset of anticyclonic wave breaking in the Eastern Pacific, as on the anticyclonic shear side of that big jet with the deep low and the Aleutians. You can see ridging. There's warm advection into the ridge at 700 millibars. The warm advection is actually advanced east of the crest of the ridge and is in the northwesterly flow. And that's another clue that anticyclonic wave breaking is afoot. And if you look further to the south in the trough off Baja, offshore, there's cold advection going in, which suggests that trough will continue deepening to the south, while the ridge will keep building to the north because of the fact that the thermal trough leads the height trough in both the ridge and the trough. All right, so now let's shift. Let's go again to the next one, which is the same time, but now we're shifting to the North American view. Randy, everybody with me? Okay.
Yep, looks good.
Okay, so now this is the same time period, same date, same time period. We're now in North American view, and you can see a little bit better structure of the subtropical jet that's coming in over Baja in there, and you can see the deepening trough off the west coast. Okay, so now let's go to the 11th, 12 hours later, in through here, and now you see how the ridge is folded over and has reached the Washington State. In there, but now if you look at the 700 millibar flow and the implied by also the surface flow, the winds are now north-northeast geostrophically, and you've got a deep cutoff off the coast of California, and the jet has strengthened. So now you are in a position, getting yourself in a position to tap moisture from the eastern tropical Pacific, and that's going to be one of the factors, as I'll show you, that was in play in this particular event. So now let's advance ourselves to the 12th. Let's see, is that the next one, the 12th?
0Z on the 12th.
Yep, okay. So if we look at 0Z on the 12th, note the tightening, the cutoff has developed. It's near San Diego, and now you're pulling water vapor, or precipitable water value, up across extreme northwestern Mexico into southwestern Arizona and extreme Southern California, with a suggestion of wrapping around a developing dry slot in there. And you've got also a 70 to 80 meter per second jet streak coming in across Baja and northern Mexico, which is suggesting that you could wind up getting a lee trough, but much further to the south and through here. So now let's go to 0Z on the 13th and through here. And so this is 18 hours before the storm is deepest. And what you see is, if you look at the surface trough that has developed to the lee of the Mexican mountains in through here, in conjunction with the subtropical jet coming across the mountains in there. And then, in a classic lee cyclogenesis event, where's the cold high? I mean, when you look at that map, and it's like the old Wendy's commercial. Where's the beef? Where's the cold high? There's no cold high to the north. I see a closed 1,000 millibar low sitting up over north of North Dakota. There's no big cold push here. So the gradient is being established by strong pressure falls to the south, because that's where the deep trough is, in conjunction with the subtropical jet. So the first important takeaway here, well, that's really the second. The anticyclonic wave breaking is the first important takeaway. And this is a subtropical jet-driven storm, not a polar front jet at all, and not something associated with extreme baroclinicity associated with a cold air outbreak in there. And when you saw the business previously with where the severe weather was reported, you can see there's a nice surge of moisture coming up across the high plains out ahead of that jet streak. So now if we go to the 14th at 00Z, we now have, this is 6 hours after the time it's deepest. So we've got the system very strong in Colorado, and it's now moving off to the northeast, and the moisture is being pulled well northward up across the Mississippi Valley, but the storm is not as deep. And then if we go to 0Z on the 15th, as we get to the Great Lakes, note that's like 1,099. That's about a 988 low. So that thing has filled almost 20 millibars since it was in southeastern Colorado. And again, there's cold advection behind this system, but the biggest thickness, I see a 522 thickness contour at the North Dakota border. Again, no big strong push. As the ridge pushed in, you got anticyclogenesis over the higher terrain of the west, but this is a Pacific air mass. This is not an Arctic air mass that's built in. So that's on the large scale. So what we need to do now is start looking at some of the smaller scale features and some of the other kinds of features. So let's go back and take a CONUS view on the next slide for the 0Z, the 13th of March. Everybody with me?
Yep, looks good.
Okay, so the left panel is just like what the left panel was on the previous one, but for the CONUS view. But the right panel is different. The right panel is 500 millibar heights, vorticity in the reds. The first shading is 6 units of vorticity, starting with a light yellow. And when you're up into the deep reds, you're at like 20, 24, and 28 in through here. And the wind barbs are in there. And all the blue is the layer mean ascent between 6 and 400 hectopascal. So that's how we calculate this. So you can see where the strong ascent is on the forward side of the trough, ahead of the subtropical jet and ahead of the surface trough. But what I want you to take note in through here is that trough that's coming across Arizona that you see, that's the trough that formed off the California coast in response to upstream anticyclonic wave breaking. But note that there's another player here, and there's a second trough coming in across Northern California and Nevada. So how many times, this is something we see in the East and Midwest a lot, but you don't see that as much on the West Coast when you have trough phasing. So you've already got the southern trough has all the moisture and the subtropical jet, but the northern trough has some additional baroclinicity, and so these troughs are going to phase. And so if we go 6 hours forward to 6Z on the next slide, you can see how the southern trough is moving to the east and beginning to lift to the north, but the northern trough is catching up with it. And there's also a separate area of ascent associated at the leading edge of the vorticity nose with the northern trough. And if you look very carefully on the left, you can see there's a little jetlet associated with that on the California coast. But you look at that, and that's not a particularly deep cyclone. That's a little closed 992 cyclone at 6Z, a contour 992. And this cyclone is going to deepen 22 hectopascals in the next 12 hours. That's not too shabby. So let's look at 12Z. So you can see the rapid deepening is taking place right in eastern Colorado. This is the bomb cyclone, very unlike a classic Lee cyclone. And you can see in the 500 millibar map, notice how we required a negative tilt and through here is the upstream trough begins to phase with the initial trough and associated with the subtropical jet. It's taken on the classic bomb tilt of northwest to southeast trough axis, which then provides very, very strong differential cyclonic vorticity advection. And you can even begin to see the wraparound in the blue field, which is noisy because it's the vertical motion field, but you can see the hook, the cyclonic wraparound of that's occurring with that. So let's go to the time of deepest flow, which is at 18Z, which is the next slide. In there, and you can see how the ascent is wrapped completely around in that, and we've got this big cyclone in there, and very, very strong winds associated with that feature. And the other thing that I haven't pointed out is note the jet to the north of North Dakota in there. If we go back one, the 12Z, the strongest wind up there was the second blue, 40 to 50 meters per second. Go forward to 18Z, and now we've got 70 to 80 meters per second in there. So in the ridge, in the downstream ridge there, you're developing a jet. So the interesting thing is what to think about, which we're going to get to, is what's going on with that development of that big downstream ridge, and we're going to see that it's going to be related to warm air advection and the strong outflow of tropical air. Okay, so we go to 00Z on the 14th. There's strong jets there. Now you have this big cutoff. The storm has used itself up when it's no longer deepening. In fact, it's beginning to weaken as it moves away from the mountains. You can see the cutoff cyclone out 500 millibars doesn't have that structure of a rapidly deepening system. System that now is really wrapped around in a broad cyclonic arc. That's a classic signature of something that's past prime. All right. Any questions on this before we go to look at some standardized anomalies on the next set of some maps? This is a good point to ask anybody has any questions. You guys know a lot more about this kind of stuff than I do from an operational point of view, so I'm very, very much interested in hearing what other people have to say.
Yeah, any questions or comments at this time, just type them in the question window or raise your hand. We've got a shy audience today, Lance, right now.
Well, I guess I need to say something especially outrageous to get everybody mad. All right.
One thing struck me, Lance, if I could ask a quick question. One thing
that
struck
absolutely.
Me, the short time frame from when it bombed to how fast it started filling seems really unusual.
Yes, agreed.
It's such a short window. Have you ever seen anything quite like that?
No, it's a very short window, and my hypothesis, and this may be wrong, and as most hypotheses are, that's what you start with. My hypothesis is that this thing responded more to thermodynamic forcing associated with diabatic heating, as we're just about to discuss, rather than baroclinicity. In other words, the baroclinicity is not extreme because there's no big cold high.
Yep. Okay. We do have some hands raised. Matt.
Okay, good. Somebody always has to ask the first question.
Right. All right, Matt, you're unmuted.
Okay, so Lance, in your experience with bomb cyclones, do most of them develop because of latent heat release? And if that's the case, then that kind of would make sense in this case, since it was further south, it had closer access to all that moisture from the Gulf of Mexico and the tropics.
Yeah, that's the next topic that's going to come up for discussion. On East Coast, classic East Coast bomb cyclones, it's like on average 2 parts dynamics and 1 part thermodynamics, especially if it's like over the Gulf Stream. So the extra, it's like when you can get tropical moisture involved, it's like turbocharges everything. But in this particular case, what's striking is how moist it is, which I'm going to about show you very soon, and how unbaroclinic it is. I mean, there's baroclinicity there, but it's almost like 1 in 1. So I think the testable hypothesis would be what made this cyclone so atypical was the importance of moisture of tropical origin that got into the circulation.
Great, thank you. We have another one, question from Paul Wolin. Paul, you're unmuted.
Yeah, hey. excuse me, this isn't a question, this is a comment about this. This is a success for the numerical models and forecasting. The morning this event, it was actually 40 degrees and raining even over Monument Hill area, and schools closed based on the forecast. And then when finally things wrapped up at 9:30 and it rapidly turned over to snow, the kids were home instead of in school, or trying to get them home in blizzard conditions. So this was just a NWP success. Unfortunately, people have to do, make a living. So some people got stuck on I-25 over Monument Hill, but they knew the conditions were coming. And also want to add that the Colorado Springs set their record wind gust of 96 miles an hour with this event.
Yeah. Very, 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 very strong winds because of the rapid deepening, of the system. Yeah. We can have very successful forecast, but a certain percentage of the population is always trying out for the Darwin Awards, no matter what you do or how good the forecast.
All right, looks like we have one more, Lance. This is from John Stopcotti. He asked, was there a barrier jet along the lee of the Rockies that played a factor?
Don't know yet. I have not seen a high-resolution simulation of this kind of event, but that's a logical question to ask, and it's a logical inference to make. Would not have surprised me in the least that it's there. But I can't tell that from these quarter-degree CFSR type analyses.
Okay, great. That was all the questions we had for now.
Okay. All right, so now let's look at some standardized anomalies. On the left is the 250 millibar heights. We're back to 0Z the 13th. And there's the standardized wind speed anomalies and are in color and shaded in sigma. And on the right is the 700 millibar heights in black and wind barbs, and standardized precipitable water anomalies shaded in sigma. So the first thing to note is this thing with that southern trough as it's coming in, you've got a small little pocket of 3 to 4 sigma wind speed in there, but you've got a much broader area of 2 to 3 sigma. So this is a pretty strong subtropical jet and a very sharp trough that's coming across Gulf of California and northwestern Mexico. And if you look at the precipitable water, my goodness, you've got the gray and then the lighter gray. You're over 6 sigma in there. 6 sigma. This is not just an ordinary event. This is really tapping remarkably moist air from the tropical Eastern Pacific on this particular case. And if we go forward to 6Z, you can see how at 250 millibars, the trough is beginning to acquire a negative tilt as the phasing continues. But there's the corridor 5 and 6 sigma wrapping from the Texas Panhandle, wrapping in towards southeastern Colorado in there on the north side, ahead of the upper level trough, and on the north side of the cyclone that's going to start rapidly deepening at this particular time. And if we go to the next time period, which is 12Z on the 13th, and you can see how the wraparound moisture, and you got a big area now of between 5 and 6 sigma, northeastern Colorado, southern Nebraska, and beginning to wrap around. And you can see how the dry slot is really developing in there in the precipitable water field. And if we go to the time of greatest depth, this is a kind of classic signature you see with a bomb cyclone on the east coast of North America or the east coast of Asia, or the rare Great Lakes kind of bomb cyclone. And I love the left-hand panel. Look how you've shortened the wavelength of the trough and ridge. And from a dynamics point of view, if you look up, let's stare at the left panel for the moment. The trough axis is east-west pretty much across Kansas, and the ridge axis is pretty much east-west across South Dakota. So from the point of view of an air parcel, you're going from a high vorticity environment over Kansas to a low vorticity environment over South Dakota very quickly. So from a Lagrangian perspective, if you're going from if you're an air parcel, from the point of view of an air parcel in that flow, you are losing vorticity like mad as you go from the trough to the downstream ridge over South Dakota, ridge axis. That means there has to be massive upper level divergence to account for the vorticity loss in that region. And that is playing a role in the development of the downstream ridge. Note what the standardized anomaly at 250 is in the jet in there. There's a little small pocket of 3 to 4 sigma in the total wind speed. Now, if we go back one time frame to 12Z, look at the change in the standardized anomaly in the wind speed at 250 millibars between 12Z and 18Z. If we go back one more to 6Z, it was the downstream one, but by 12Z, the ridge is sitting there over Great Slave Lake in there. It's like 2 sigma, but note the rapid growth, new growth, because if you look over at 12Z, you see the jet core is over southern Hudson Bay in there, and there's a small area of 2.5 to 3 sigma. But that's not what's going to intensify. When you look at 18Z, you can still see the original jet streak across southern Hudson Bay, but the new one that's developed north of North Dakota and Minnesota is the one I'm referring to in there, and that is rapid growth of what used to be over eastern Montana and North Dakota at 6 hours earlier. And then if we go further, at 00Z on the 14th, you've got a large area there of 3 to 4 sigma, even 4 to 5 sigma, a couple in there in that jet. So one of the things that people aren't necessarily paying attention to through here is massive jetogenesis that's taken place in the crest of that ridge, and that has to be linked to what's going on upstream with the cyclone. And if you look at the anomaly precipitory, there's a classic. When you talk about a T-bone structure in there, that's really remarkable on that particular time period. All right. So before we go into the next series of things, are there any questions on the standardized anomalies that anybody would like to address?
Any questions or comments? Raise your hand or type in the question window. Nothing seen on that one, Lance.
Okay. Let's go to the next one, which is another CONUS overview back on the 13th. And now things get a little bit more complicated. I have contoured on here potential vorticity, layer mean potential vorticity between 3 and 200 millibars. Those are the solid contours. The irrotational wind are the vectors, and the reference scale is on the 10 meter per second down there. I always like to use the stream function and velocity potential to map the non-divergent wind and the divergent wind, because the geostrophic wind is only non-divergent if you don't allow for the variation of the Coriolis parameter. There's some divergence in the geostrophic winds. So in other words, a partition between the geostrophic and ageostrophic wind is not clean, but a partition between the non-divergent wind as measured through the stream function and the divergent wind as measured through the velocity potential is clean. So what we have here is calculated from the velocity potential, which I'm not displaying, what the irrotational wind is. So this is the divergent component of the wind. And why that matters is because jets will occur where there are PV gradients. And it's very important to understand what the advection of potential vorticity is by both the non-divergent and the divergent wind components, and how that tightens and weakens PV gradients. And red ascent is between 6 and 400 millibars on the red contours, and the 250 millibar jet is shaded in the color bar. And on the right-hand side, I've repeated the 300 to 200 layer mean potential vorticity in gray, and the shear between 850 and 200 is a barb, so that's the shear. The minimum sea level pressure centers are located in the red numbers, And then the coupling index is what's shaded, and that may be something that's probably not familiar to many people. But I like the coupling index. Gary Lackman and I wrote a paper back in 1995 on a inland re-intensification of a tropical cyclone, and we created this what we called the coupling index, which is a measure of the deep tropospheric stability. Basically, what it is the difference between the equivalent potential temperature at 850 hectopascals and the potential temperature on the dynamic tropopause. And so when that number is negative, that indicates real deep stability through the troposphere. And the reason we use the potential temperature on the dynamic tropopause is that's readily contoured, and on the dynamic tropopause, the difference between the theta and theta E at that elevation is basically zero. So theta E at 850 and difference between theta on the dynamic tropopause and theta E at 850 millibars is what we call the coupling index, and that's what's shaded. So you can see, if you look on the left panel, you can see the potential vorticity maximum over Arizona associated with the trough that we've been talking about. You see the gradient way up north of the U.S. of Great Slave Lake. You see the PV gradient in the ridge, which is associated with where the jet's going to be. And you can see all the red, which is on the left panel, which is the strong ascent on the forward side of the PV max there. And you can see the strength of the diabatically driven outflow by the length of those irrotational wind vectors in there. And basically, the irrotational wind vectors in Arizona are directed, in New Mexico are directed to the west-southwest in there, which is helping to tighten the PV gradient in that region. But if you look on the right, on the coupling index, note that you've got a big area between 0 and 5. So you have relatively unstable air sitting in the core of that trough, but you also have a pretty big area of dark blue western Kansas and southeastern Colorado. So this deepening storm has access to air that has a marginal stability through the deep troposphere between 850 and the dynamic tropopause. And note there are also a few pockets of yellow, which are negative values of the coupling index. So when I look at this, I see, this storm has the potential for very vigorous vertical motion in there because of the very low values of the coupling index. So if we go to 6Z now, and through here, now note that the trough is beginning to acquire a negative tilt. And through here, note the length of the irrotational wind vectors has lengthened, directed to the southwest, and that some in that ascent band are directed to the southeast. So picture that, and that note the ascent band from across the Texas Panhandle and down into West Texas in there, and then extending up towards northeastern Colorado. The red's getting stronger in there, but note the arrows of the irrotational wind further to the south and across the Oklahoma Panhandle down into Texas. Those arrows are directed to the southeast, while the arrows are longer and directed to the southwest. So that is the beginning of a strong divergent outflow. When the irrotational wind vectors start to show divergence like that, that means that you're starting to get some vigorous ascent. And where is that occurring? Right above, if you look to the right panel, where we have deep blue values of the coupling index. So let's go forward to 12Z. And now you're starting to see the classic signature of a bomb cyclone. Note the difference in the orientation of the irrotational wind vectors between 6 and 12Z. It starts to look like a starburst pattern in through here, and that is the classic signature of a rapidly deepening cyclone in which air is coming in, up, and out, and the out is strong divergent outflow in there. And what that is doing then is going to start producing changes in what the PV structure looks like. And also, if you look like even in southeastern Colorado now at 12Z, you're starting to see some negative values of the coupling index that are really developing. Now for the grand event, go to 18Z. Now there's what I call your classic starburst pattern. in there. And first, let's just look at the coupling. Let's look at the coupling. It's cleaner for the moment. Look how the PV hook has developed. Note the atmosphere, the classic PV hook in the PV field developed to the east as it pulls northward. So the atmosphere is playing hooky in through here, and that PV hook. And so people will say, well, the PV hook is a classic signature of bomb cyclogenesis, but basically the barn door is wide open at this point. So if you're not paying attention and you say, oh, why is that hook there? You've already missed all the major action. So this is a storm at maximum depth in there. But note that the negative value of coupling index has wrapped around all the way to the west side into eastern Colorado. And so there's this narrow corridor of very unstable air in there that's wrapped around, which will facilitate rapid intensification, help to facilitate the rapid intensification of the cyclone. Now note, if we go back to the left panel, and note that we have as the jet in there, what's happening across the Dakotas and Montana into southern Canada. Note that the irrotational wind vectors are directed from lower values of PV to higher values of PV. And so what that's telling you is that you're strengthening the PV gradient by negative PV advection by the irrotational wind from Montana up into southern Canada, and that's consistent with the strengthening jet. So see that. Let's go back one panel to 12Z. So if we go back to 12Z, the jet's weaker up there, but note that you don't see a lot of negative PV advection by the irrotational wind just yet at 12Z. But now let's go back to 18Z. Now note you've got negative PV advection by the irrotational wind over a wide area from Wyoming all the way up into Canada in there, and the jet is intensifying in response to negative PV advection by the irrotational wind. Now if we go to 00Z in there, and the jet's even stronger in there, and note that, again, it has that classic signature, but now you've already achieved maximum intensity, and there's your PV hook, and there's your life cycle of the cyclone. So before we go on, getting towards the end in here, towards the next set of maps, I'm sure there's got to be some questions about this, because these are some maps that you guys are probably not as familiar or used to looking at. So holler and scream.
All right, questions, comments. Matt Bunkers, you're unmuted. Oh, you're self-muted, Matt.
Okay, gotcha. I'm not familiar with the irrotational wind. How is that calculated again?
You calculate you calculate the stream function, and then from that you just invert it, because the stream function, the vorticity is the Laplacian of the stream function. So then from the vorticity you calculate the stream function, from the stream function you calculate the non-divergent part of the wind, and the divergence is the Laplacian of the divergent part of the flow, the velocity potential. And so you invert that, and you get the divergent part of the wind. You know what the geostrophic vorticity is? The geostrophic vorticity is the Laplacian of the high field, right?
Yes.
Okay, so the actual relative vorticity is the Laplacian of the stream function, but the stream function is defined by the non-divergent wind. That's why it's clean. So that's the total non-divergent part of the flow is defined by the stream function. The divergent part of the flow is defined by the velocity potential.
Okay, so the irrotational wind then represents the divergent part
That's
of
right.
the wind?
That's right. Okay. Exactly. And we map it by vectors in there. You could also put contours on it and so on, but one of the problems with these kinds of maps is you start layering on a lot of different fields, and then people's eyes can glaze over. But I'm totally used to these kinds of maps because we use them in research and teaching and all that kind of stuff all the time. So when you see a starburst pattern, any storm that has a significant convective part for rapid intensification, virtually every single bomb cyclone anywhere on the planet will have a starburst pattern looking like the map at 18Z and the 13th for the irrotational wind vectors. They all go out in a starburst pattern. A frontal band, for example, irrotational wind vectors in a classic linear cold front will be linear. They'll be, say if you have a north-south cold front running from, I don't know, Minnesota all the way down to Texas in there, and there's all kinds of rain along that cold front, on the west side of the cold front, the irrotational wind vectors will all be directed to the west, and on the east side of the cold front, they'll all be directed to the east, but you won't see a starburst pattern. It'll be a linear pattern, and that's a characteristic signature when you have a lot of stratiform precipitation along the front. But when you have a lot of convective type of precipitation concentrated in certain areas in one particular region, you get this classic starburst bomb-like pattern. So that's the signature in the irrotational wind field. A starburst pattern like you see at 18Z on the 13th is a classic signature of a rapidly intensifying cyclone.
Awesome. Thanks, Lance. That was only question for this section.
Okay. So let's look at a water vapor loop. And through here, it should play. If you go to the next.
Yeah, it's looping well.
Is it playing? Yeah, and you can see the phasing, and you can see how you can see the development of the PV hook. Look at the phasing that comes on in there, how the troughs begin to phase, and the negative tilt of the trough, and the wraparound, dry slot, all that we've been talking about going on, and then watch what goes on. And look at several levels and look what goes on, far away and close in, and so on. So you've got an awful lot of dynamics and thermodynamics going on this map. But once you really get up close and personal with all the maps and charts we just talked about, and by the way, people, Randy, make sure people get those links that I sent you, because you can actually look at all the raw maps in which these analyses are made. And people can look at them at their leisure.
I'll be sure to share those.
Yeah, so that is a beautiful example. I'm indebted to Dan Lindsay at NOAA CIRA in Fort Collins for providing these nice, beautiful loops in there. All right, so let's start summarizing some of these things. And through here on the next slide on conclusions, and through here. The Eastern Pacific anticyclonic wave breaking allows a deepening downstream West Coast trough to trap moist subtropical air. That's critical to get that in. And the West Coast trough interaction then with the strong subtropical jet stream enables a surge of deep tropical moisture to reach the southwest. But the initial thing that gets it going here is the anticyclonic wave breaking in the Eastern Pacific. Lee cyclogenesis over northern Mexico and western Texas occurs in this moist air mass ahead of the West Coast trough, and the anticyclonic wave breaking continuing over the Eastern Pacific enables a second trough to merge with the West Coast trough, resulting in explosive Colorado Lee cyclogenesis. And that leads, if we go to the next slide, two testable science hypotheses. And this case I think this case should eventually get in the literature, and it's worth writing up and doing this and working with it further. So the pair of science hypotheses that I put out there for testing that trough interaction, cyclonic wave breaking, and PV anomaly merger promotes exceptionally strong Colorado Lee cyclogenesis in through here, the downstream cyclonic wave breaking, and that diabatic processes associated with a subtropical moisture surge intensifies cyclonic wave breaking related ascent and turbocharges Colorado Lee cyclogenesis. So those are my two science hypotheses for the actual rapid deepening of the storm. There'd be a third hypothesis that anticyclonic wave breaking in the Eastern Pacific made it all possible for this to happen. So are there any questions or issues with the
any questions, comments, raise your hand or type in the question window. We have one from Mike Fowle, Lance.
Okay.
He asked if you could comment on the predictability of this particular bomb in numerical weather prediction. He comments, due to the amount of jet/moisture phasing, would assume that it was fairly low.
Well, actually, the forecast, once they locked into it within 3 to 4 days ahead of time, did a reasonably good job on this particular event. But there wasn't really much lead time, like out at day 8, 9, and 10. So if you were looking at, say, week 2 type of predictability for this kind of event, it was very, very limited. My experience with the GEFs, the current version of the GEFs, Alicia Bentley, my former PhD student who's now at NCEP, has shown me some test cases of the GEFs, the new GEFs version 12, which will be a 30-member ensemble plus a control member, relative to the current 20-member ensemble with a control member. Is doing a much better job at getting some of these things. But my experience with the current GEFs is it doesn't really start locking on to what's going on. First of all, it's 200 dispersive, but it doesn't really start locking on until about 120 to 144 hours. And even then, in certain things, it's like I don't really begin to trust it until about 96 to 120 hours. But every case is different. But in general, when you have tropical air involved in a cyclogenesis event, predictability is limited relative to predictability of a strongly baroclinic, moisture-starved type of, say, Alberta Clipper cyclone or something like that.
Okay, great. Thanks, Lance. I know we'll be looking at the version 12 of the GEFs, and this is, I know, one of the retrospectives that Jeff Manikin's group ran, so we're curious to get a look at that. We're going to be reviewing that here in the next couple weeks, actually, so it's interesting to hear that Alicia's looked at that. I see no other questions. Any other last call for questions for Lance?
I'll just point out that if you go